Section 1.5, Solving Trig Equations with Calculators, Part 1. In the previous section, we started solving trig equations. The only problem with the equations we solved in there is that they pretty much all had solutions that came from a handful of standard angles. And of course, there are many questions out there that simply don't. So in this section, we are going to take a look at some more trig equations, the majority of which will require the use of a calculator to solve. A couple won't need a calculator. The fact that we're using calculators in this section does not, however, mean that the problems in the previous section aren't important. It is going to be assumed in this section that the basic ideas of solving trig equations are known and that we don't need to go back over them here. In particular, it is assumed that you can use a unit circle to help you find all the answers to the equation, although the process here is a little different, as we'll see. And it is assumed that you can find answers in a given interval. If you are unfamiliar with these ideas, you should first go to the previous section and then go over those problems. Now, before proceeding with the problems, we need to go over how our calculators work so that we can get the correct answers. Calculators are great tools, but if you don't know how they work and how to interpret their answers, you can get in serious trouble. First, as already pointed out in previous sections, everything we are going to be doing here will be in radians, so make sure that your calculator is set to radians before attempting the problems in this section. Also, we're going to use 4 decimal places of accuracy in the work here. You can use more if you want, but in this class we'll always use at least 4 decimal places of accuracy. Next, and somewhat more importantly, we need to understand how calculators give answers to inverse trig functions. We didn't cover inverse trig functions in this review, but they are just inverse functions, and we have talked a little bit about inverse functions in the review section. The only real difference is that we are now using trig functions. We will only be looking at 3 of them, and they are inverse cosine. So cosine inverse of x is the same thing as arc cosine of x. Inverse sine, sine inverse of x is the same as arc sine of x. And inverse tangent, tangent inverse of x is the same as arc tangent of x. Now, as shown, there are 2 different notations that are commonly used. In these notes, we'll be using the first form since it is a little more compact. Most calculators these days will have buttons on them for these 3, so make sure that yours does as well. We now need to deal with how calculators give answers to these. Let's suppose, for example, that we wanted our calculator to compute cosine inverse of 3/4. First, remember what the calculator is computing is the angle. So let's say x that we would plug into cosine to get a value of 3/4. Or x is equal to the cosine inverse of 3/4, which means the cosine of x, which is equal to 3/4. So in other words, when we are using our calculator to compute an inverse trig function, we are solving a simple trig equation. Having our calculators compute cosine inverse of 3/4 and hence solve cosine of x equals to 3/4 gives the following result. X is equal to cosine inverse of 3/4, which is equal to 0.7227. So let's take a look at the calculator here. Well, first, let me put this on. Right above the sine, the cosine, and tangent, you will see inverse sine, inverse cosine, and inverse tangent. Okay, and then we want to make sure that everything is in radian measure, so if we take a look here, we got to make sure that this is highlighted, which it is. So let's go ahead and find out the cosine inverse of 3/4. If we put second cosine inverse, put in our fraction 3 divided by 4, then to 4 decimal places we get 0.7227. Now, from the previous section, we know that there should in fact be an infinite number of answers to this, including a second angle that is in the interval between 0 and 2 pi. However, our calculator only gives us a single answer. How to determine what the other angles are will be covered in the following examples, so we won't go into detail here about that. We did need to point out, however, that the calculators will only give a single answer and that we're going to have more work to do than just plugging a number into a calculator. Since we know that there are supposed to be an infinite number of solutions to cosine of x equals 3/4, the next question we should ask then is just how did the calculator decide to return the answer that it did? And why this one and not one of the others? Will it give the same answers every time? There are rules that determine just what answer the calculator gives when computing inverse trig functions. All calculators will give answers in the following ranges. Cosine inverse of x would be in between 0 and pi. Sine inverse of x is going to be in between negative pi over 2 and positive pi over 2. And tangent inverse x is going to be in between negative pi over 2 and pi over 2, but it doesn't include it. Now, if you think back to the unit circle and recall that we think of cosine as the horizontal axis, then we can see that we'll cover all possible values of cosine in the upper half of the circle. And this is exactly the range given above for the inverse of cosine. Likewise, since we think of sine as the vertical axis in the unit circle, we can see that we'll cover all possible values of sine in the right half of the unit circle, and that is the range given above. Now for the tangent range, look back to the graph of the tangent function itself, and we will see that one branch of tangent is covered in the range given above, and so that is the range we'll use for inverse tangent. Note as well that we don't include the endpoints in the range for inverse tangent, since tangent does not exist here. There. So, if we can remember these rules, we will be able to determine the remaining angle between 0 and 2 pi that also works for each solution. So as a final quick topic, let's note that it will on occasion be useful to remember the decimal representations of some basic angles. So here they are. Pi over 2 is equal to 1.5708. Pi is 3.1416. 3 pi over 2 is equal to 4.7124. And 2 pi is equal to 6.2832. Now using these, we can quickly see that the cosine inverse of 3/4 must be in the first quadrant, since 0.7227 is between 0 and 1.5708. This will be of great help when we go to determine the remaining angles. So once again, can't stress enough that calculators are great tools that can be of tremendous help to us, but if you don't understand how they work, you will often get the answers to problems wrong. So with all that out of the way, let's take a look at our first problem. We want to solve 4 times the cosine of t, which is equal to 3, on the interval between -8 and 10. Okay, so the first step here is identical to the problems in the previous section. We first need to isolate the cosine on one side by itself, and then use our calculator to get the first answer. So we divide both sides by 4. We want to get cosine of t, which is equal to 3/4. To solve for t, that means we're dividing by cosine of t, which means t is going to equal the cosine inverse of 3/4, which gives us 0.7227. So this is the one we were using above in the opening discussion of this section. At the time, we mentioned that there were infinite number of answers, and that we'd be seeing how to find them later. Well, that time is now. So, first, let's take a quick look at the unit circle for this example. Here is 0.7227. The angle that we found is shown on the circle, as well as the other angle that we know should also be an answer. Finding this angle here is just as easy as in the previous section. Since the line segment in the first quadrant forms an angle of 0.7227 radians with the positive x-axis, then so does the line segment in the fourth quadrant. This means that we can use either negative 0.7227 as the second angle, or 2 pi minus 0.7227, which is equal to 5.605. Which you use depends on which you prefer. We'll pretty much always use the positive angle to avoid the possibility that we'll lose the minus sign. So all possible solutions, ignoring the interval for the second, are then t, which is equal to 0.7227 plus 2 pi n, and t is equal to 5.605 plus 2 pi n. Now all we need to do is plug in the values of n to determine the angle that are actually in the interval. And here's the work for that. If we plug in n is equal to -2, well, t is equal to -11.8 1.8437. That's not a solution, but negative 7.0059 is. Plugging in negative 1 for n, t is equal to negative 5.605 and negative 0.7227. When n is equal to 0, t is equal to 0.7227 and 5.605. And when n is equal to 1, t is equal to 7.0059. And we know that this is not a solution, 11.8437, because those are outside of the interval. So the solution to this equation in the given interval are the ones that we have solved for. Now note that we had a choice of angles to use for the second angle in the previous problem. The choice of angles, there will also affect the values of n that we'll need to use to get all the solutions. So in the end, regardless of the angle chosen, we'll get the same list of solutions, but the values of n that give the solutions will be different depending on our choice. Also in the example above, we put in a little more explanation than we'll show in the remaining examples in this section to remind you how these work. So for example 2, we're going to solve negative 10 cosine of 3t equal to 7 on the interval between negative 2 and 5. Okay, let's first get the inverse cosine portion of this problem taken care of. We divide both sides by negative 10, and then we're going to take the inverse cosine. So it's going to be 3t, which is equal to the cosine inverse of negative 7 over 10, and don't forget divide by 3. So let's do this on the calculator here. So we have the cosine inverse. So let's find the second cosine inverse of negative 7 divided by 10. Okay, that's 2.346. But then remember that we need to divide by 3. So dividing by 3 is going to give us 0.7821. Now let's look at a quick unit circle for this problem. As we can see that the angle 2.3462 radians is in the second quadrant, and the other angle that we need is in the third quadrant. We can find this second angle in exactly the same way we did in the previous example. We can use either negative 2.3462, or we can take 2 pi and subtract 2.3462 to get 3.9370. As with the previous example, we'll use the positive choice, but that is purely a matter of preference. You could use a negative if you want to. So here's your angle, and then there is the negative version of it. So now let's finish out the problem. First, let's acknowledge that the values of 3t that we need are the following. And we can now divide both sides by 3. I know that we did that on our calculator, but you can see here where we get 0.7821 is down here by dividing by 3. But that means you also need to divide 2 pi n divided by 3. So that's why you want to wait until you get to this part to divide both sides by 3. So now we have our two angles divided by 3. So here are our 2, plus 2 pi n over 3, plus 2 pi n over 3. And finally, we just need to get the values in the interval. So remember that what was our interval from this question? If we go back to the question, it's in between negative 2 and 5. So we got n is equal to negative 2. Plug our values in. Well, these two values have to be excluded. Plug in negative 1. We get our two values for t. Plug in 0. We get our two values for t. Plug in 1. We get our two values for t. Plug in 2. We have one value, and then exclude the second value. So that tells us that these numbers here do not fall within the interval of negative 2 and 5. So that's why these are not part of the solution set. So the solutions to this equation in a given interval are the following. Now we've done a couple of basic problems with cosines. Now let's take a look at how solving equations with sines work. So for example 3, we want to solve 6 times the sine of x over 2 which is equal to 1, on the interval between -20 and 30. So let's get the calculator work out of the way, since that isn't where the difference comes into play. So the sine of x over 2 is equal to 1 over 6. We divide both sides by sine, so we get x over 2, which is equal to the sine inverse of 1 over 6. And the sine inverse of 1 over 6 is equal to 0.1674. So there's the one angle, and then there's the other angle. So there's the unit circle for this example. Now, to find a second angle in this case, we can notice that the line in the first quadrant makes an angle of 0.1674 with the positive x-axis. And so the angle in the second quadrant will then make an angle of 0.164 with the negative x-axis. So if we start at the positive x-axis, we rotate a half a revolution and then back off of 0.1674. Therefore, in this case, we're ending up with pi here. So since we have pi here, that's why we're taking pi and subtracting 0.1674 to get 2.9742. So here's the rest of the solution for this example. We're going to assume from this point on that you can do this work without much explanation. So keep in mind here that what we're doing is we're multiplying both sides by 2 to get the following result. Same thing over here. We're multiplying both sides by 2 to get the following result. Now we have our angles plus 4 pi n plus 4 pi n when n is equal to the following numbers. So when we plug in from -2 to +2, we can see that our interval, we wanted to make sure that our interval was in between -20 and 30. Oops, wrong way. So we're going to exclude everything that's outside of this interval. So this is outside and this is outside. And then by plugging in all these numbers, then we get our following results. Example 4, it says solve 3 times the sine of 5z is equal to -2 on the interval between 0 and 1. So you should be getting pretty good at these by now, so we won't be putting much explanation in for this one. So here we go. The sine of 5z is equal to -2/3. Divide both sides by the sine. So 5z is equal to the sine inverse of -2/3. Now plugging this into our calculator, we get -0.7297. So there is our angle. We want to find this angle. Okay, with this one, we're going to do a little more work than with the others. So for the first angle, we could use the answer our calculator gave us. However, it's easy to lose minus signs, so we'll instead use 2 pi minus 0.7297 to get 5.5535. Again, there's no reason to this other than a worry about losing the minus sign in the calculator answer. So if you'd like to use the calculator answer, you are more than welcome to. For the second angle, we'll note that the lines in the third and fourth quadrant make an angle of 0.7297 with the x-axis. So if we start at the positive x-axis, we rotate a half revolution and then add on 0.7297 for the second angle. Therefore, the second angle is pi plus 0.7297, which is 3.8713. So here's the rest of the work. So here are our numbers, plus 2 pi n plus 2 pi n. Again, we're multiplying both sides by 5 to get this result. So we get z, which is equal to 1.1107 plus 2 pi n over 5. Z is equal to 0.7743 plus 2 pi n over 5. And then we're going to find out when n is equal to -1 and when n is equal to 0. And then I believe the interval was between 0 and 1. So we know that since it's got to be in between 0 and 1, we cannot include that point, that one, or that one. So in this case, we get one single solution of 0.7743. Now note that in the previous example, we only got a single solution. This happens on occasion, so don't get worried about it. Also note that it was the second angle that gave us this solution. And so if we just relied on our calculator without worrying about other angles, we would not have gotten this solution. Again, it can't be stressed enough that while calculators are a great tool, if we don't understand how to correctly use the result, we can and often will get the solution wrong. To this point, we've only worked examples involving sine and cosine. Let's now work a couple of examples that involve other trig functions to see how they work. Example 5. Solve 9 times the sine of 2x, which is equal to the negative 5 times the cosine of 2x on the interval between negative 10 and 0. So at first glance, this problem seems to be at odds with the sentence preceding the example. However, it really isn't. First, when we have more than one trig function in an equation, we need a way to get equations that only involve one trig function. There are many ways of doing this that depend on the type of equation we're starting with. In this case, we can simply divide both sides by a cosine and we'll get a single tangent in the equation. We can now see that this really is an equation that doesn't involve a sine or a cosine. So if we divide both sides by the cosine of 2x and then divide both sides on the right side by 9, then we're going to get sine of 2x over the cosine of 2x, which is equal to the tangent of 2x, which is equal to the negative 5/9. So now, dividing both sides by the tangent, we get 2x, which is equal to the tangent inverse of negative 5 over 9. Tangent inverse of negative 5 over 9 is equal to negative 0.5071. Now, the unit circle doesn't involve tangents. However, we can use it to illustrate the second angle in the range between 0 and 2 pi. So we have negative 0.5071. Now the angles that we're looking for here are those whose quotient of sine over cosine is the same. The second angle where we will get the same value of tangent will be exactly opposite of the given point. For this angle, the values of sine and cosine are the same, except they will have the opposite signs. In the quotient, however, the difference in signs will cancel out and we'll get the same value of tangent. So the second angle will always be the first angle plus pi. Before getting a second angle, let's also note that, like the previous example, we'll use 2 pi minus 0.5071, which equals 5.7761 for the first angle. Again, this is only because of a concern about losing track of a minus sign in our calculator answer. We could just as easily do the work with the original angle our calculator gave us. Now, this is where it seems like we're just randomly making changes and doing things for no reason. The second angle that we're going to use is pi plus negative 0.5071, which is equal to pi minus 0.5071, which gives us 2.6345. The fact that we use the calculator answer here seems to contradict the fact that we used a different angle for the first above. The reason for doing this here is to give a second angle that is in the range between 0 and 2 pi. Had we used 5.7761 to find a second angle, we'd get pi plus 5.7761, which is equal to 8.9177. This is a perfectly acceptable answer. However, it is larger than 2 pi, 6.2832, and the general rule of thumb is to keep the initial angles as small as possible. So here are all the solutions to the equation. Again, we're going to multiply both sides of these two equations by 2 to then get x, which is equal to 2.881 plus pi n, and x is equal to 1.3173 plus pi n. And again, let's go back to what our is between, this example has to be in between negative 10 and 0. So again, we're excluding all the values that are outside of that interval. And therefore, the 7 solutions to this equation are the following. Now note as well that we didn't need to do the n equals 0 computation, since we could see from the given interval that we only wanted negative answers, and these would clearly give positive answers. Now before moving on, we need to address one issue about the previous problem. The solution method used there is not the standard solution method, because the second angle is just pi plus the first, and if we added pi onto the second angle, we'd be back at the line representing the first angle. The more standard solution method is to just add pi times n onto the first angle. So if using the calculator answer, this would give 2x, which is equal to negative 0.5071 plus pi n. And if using a positive angle corresponding, the calculator answer would then give us 2x, which is equal to 5.7761 plus pi n. Then dividing by 2 either of the following sets of solution, we would get the following. Negative 0.2536 plus pi n over 2, 2.8881 plus pi n over 2. Either of these sets of solutions is identical to the set of solutions we got in the example. So we'll leave it to you to plug in some n's and verify that. So why did we not use the method in the previous example? Simple. The method in the previous example more closely mirrors the solution method for cosine and sine. They both generally give two sets of angles. And so for students that aren't comfortable with solving trig equations, this gives us a consistent solution method. Many calculators today can only do inverse sine, inverse cosine, and inverse tangent. So let's see an example that uses one of the other trig functions. Example 6. Solve 7 times the secant of 3t is equal to negative 10. We'll start this one in exactly the same way we've done all the others. Secant of 3t is equal to negative 10 over 7, which means 3t, divide both sides by the secant, which makes us 3t is equal to the secant inverse of negative 10 over 7. Now we reach a problem, as noted above. Many calculators can't handle inverse secant, so we're going to need a different solution method for this one. To finish the solution here, we'll simply recall the definition of secant in terms of cosine and convert this into an equation involving cosine instead, and we already know how to solve those kinds of trig equations. So rewriting secant of 3t as 1 over the cosine of 3t equal to negative 10 over 7. If we take the inverse of 1 over the cosine of 3t, we get cosine of 3t. That means we need to take the inverse of negative 10 over 7, which is negative 7 over 10. Now we solve this equation in the second example above, so we don't redo our work here. The solution is t, which is equal to 0.7821 plus 2 pi n over 3. T is equal to 1.3123 plus 2 pi n over 3. We weren't given an interval in this problem, so here there's nothing else to do. For the remainder of the examples in this section, we're not going to be finding solutions in an interval to save some space. If you followed the work from the first few examples in which you were given intervals, you should be able to do any of the remaining examples if given an interval. Also, we will no longer be including sketches of unit circles in the remaining solutions. We are going to assume that you can use the above sketches as guides for sketching unit circles to verify the claims in the following examples. The next 3 examples don't require a calculator but are important enough or cause enough problems for students to include in this section in case you run across them and haven't seen them anywhere else. I'm going to solve the cosine of 4 theta, which is equal to negative 1. There really isn't much to do with this problem. It is, however, different from all the others done to this point. All the others done to this point have had 2 angles in the interval between 0 and 2 pi that were solutions to the equation. This only has 1. If you aren't sure you believe this, sketch a quick unit circle and you'll see that in fact there is only 1 angle for which cosine is negative 1. Here is the solution to this equation. 4 theta, which is equal to pi plus 2 pi n, divide both sides by 4. Therefore, theta is going to equal pi over 4 plus pi over n over 2, where n is equal to 0 plus or minus 1 plus or minus 2. Now for example 8, it says solve the sine of alpha divided by 7 is equal to 0. Again, not much to this problem. Using a unit circle isn't too hard to see that the solutions to this equation are alpha over 7 is equal to 0 plus 2 pi n. Alpha over 7 is equal to pi plus 2 pi over 2 pi n. Divide both sides by multiply both sides by 7, we get alpha is equal to 14 pi n, alpha is equal to 7 pi plus 14 pi n, where n is equal to 0 plus or minus 1 plus or minus 2. Now this next example has an important point that needs to be understood when solving some trig equations. Example 9, solve sine of 3t is equal to 2. Now this example is designed to remind you of certain properties about sine and cosine. Recall that the sine of theta is in between negative 1 and 1, cosine of theta is in between -1 and 1. Therefore, since sine will never be greater than 1, it definitely can't be 2. So there are no solutions to this equation. It is important to remember that not all trig solutions will have solutions.